All right, I will begin with a scripture. So it's another one from Proverbs. And here it goes. Proverbs 17:10. A rebuke goes deeper into one who has understanding than 100 blows into a fool. So always an important verse to read when you're grading things. But sorry, too soon? Anyway, I'll begin with a word of prayer. Heavenly Father, we thank you again for this opportunity we have to meet and study your creation. Just pray that you would give us understanding today about momentum, and just encourage the students if they're struggling just to persevere and to do better, Lord. In your name I pray, Lord Jesus. Amen. All right, so momentum. So what's the deal with momentum? Definition: a mass m with velocity v has momentum p equals to m times v. All right. So momentum of a point mass, I mean, to be clear, here I'm talking about a hypothetical point mass. And we'll try to improve on that concept today a bit, all right? But if you had such a thing as a point mass, and it had velocity v, then its momentum is mv, all right? So for example, if I had, I don't know, let's suppose we had the velocity equals to v naught minus gt, let's say y hat, right? So this would be the velocity of a projectile. So, obligatory, there you go. So, projectile, that's the velocity, right? What's the momentum? Well, if it has mass m, then we can calculate the momentum would be mv, right? Would be mv naught minus mgt y hat. There you go. That would be the momentum. So momentum could be a function of time, right? Now, what happens if we differentiate this? What's dp dt here? We got ddt of mv naught minus mgt y hat. Of course, here I'm assuming v naught is the initial velocity. That's a constant, right? And so this differentiation is kind of boring. It just gives you back minus mg y hat. The t differentiates to 1. Everything else just rides along or goes to 0. What is that? Yeah?
I had a question about the velocity. Is that just the velocity in the y direction?
No, that's the velocity.
Interesting. And is y hat just a unit vector, or is
Uh-huh.
Oh, so it's not just the direct,
Yeah, I put vectors. So this is a vector, that's a vector, that's a vector, yeah.
okay.
If you want, I mean, I could,
Vertical.
I could, here, watch this. Z hat, Z hat, Z hat, Z hat, right?
So it's just a placeholder variable for the unit vector?
Well, I mean, it depends on what coordinate system you want to think about. If I'm thinking about z as being the vertical direction, then this is a reasonable formula for velocity, of like this marker, right? It could also have gone this way. Either way, we'd have the same, well, we'd have the same dp dt. What is that? No. Yeah.
Is it a force?
Yes, force. Yes, it is the force. So if I wrote this in the other notation, this would be 0, 0 minus mg, right? This is the force of gravity. This is not an accident. The time rate of change of momentum on a point particle is equal to the net force. That's a theorem. Theorem for point mass m, we have the net force is equal to the time rate change of the momentum, dp dt. Let's look at the proof of this theorem. Here we go. So we have ma is equal to the net force, right? But what is ma? ma is m dv dt, right? So, all right. So I can pull the m inside the derivative if what? If the mass is what? If the mass is constant, right? So for a point particle, unless you're like in Star Trek or something, the point particle's mass doesn't change, right? Like it is what it is, right? Can you think of examples where that wouldn't be the case? The correct answer to this question is I have no idea what a point mass is, so I don't know, right? I mean, a point mass is an idealization, right? It's what it's saying is all of the masses at that point, and we don't really have any mathematical description more than that to say, except that the mass is basically there. So you could think about a raindrop, right? You could think about a raindrop as a point mass, and perhaps as the raindrop traveled through a cloud, it could accrue more water, right? And then if you think of the raindrop as a mass, its mass is changing, right? So in that kind of situation, this would not be a legitimate calculation because mass would be a function of time. But here, I'm assuming a point mass, you know, of this mass is fixed, all right? If that's the case, I can bring the m inside the derivative, and that's exactly dp dt, you see? So, and that's the net force. That's the net force. And in fact, an improvement on Newton's second law really is this. So here's Newton's, second law, momentum version. Remix. There we go. So here we have, that's right, I'm your DJ. F is dp dt. There you go. This is Newton's second law in terms of momentum. So, you know, you could try to work an example. I'm not going to finish the momentum here. Excuse me, I'm not going to finish the derivation here, but let me just start something. So, like, hypothetically, if you had that, water drop, the mass at time t, is basically equal to some constant, let's say, alpha times the radius cubed. That would be the mass at time t, right? And then maybe it's falling through some cloud or something, right? And it's causing dm dt to be what? Well, it's increasing, right? And the bigger the water droplet gets, the more it's picking up the water passing through the cloud, right? So it basically would depend on the cross-sectional area of it as it hits. So that would be something like, r squared. But also, the faster it goes through, the more water it's hitting. So it probably should also have like a, dy dt. All right? And for the sake of, I'm going to take this as positive, if you don't mind. All right? So that would be a reasonable, and probably I need some constant, right? Beta. Something like that might be a reasonable model of how the water increases the mass as it falls, right? In this situation, we could write the following, right? We could write, well, the way it would work is this. dp dt is equal to the net force. Well, what's the net force? Nobody? So the thing that's making it fall is gravity, right? So at any given time, the net force would just be mg. But now m is a function of time. All right? So in this situation, we'd have ddt of mv. All right? Which would give me dm dt times v plus m dv dt equals to mg. But as I was saying, dm dt should be something like, you know, how did it go here? Beta r squared dy dt, and then this v is also dy dt plus m d squared y dt squared equals mg. So, but of course the m was what? It was alpha r cubed. And you could try to solve differential equations like this to understand the motion of a raindrop through a cloud. Now I actually do have an example like this worked out in my differential equations notes, but I just wanted to leave this here as just a sort of a starting to go down the path. Like we can't do this in here because we don't have differential equations, right? We can't complete this thought, but you could if you had a variable mass. What you do is you put dp dt equal to the net force and you work out the calculus, all right? It's one of the reasons you need to take differential equations as an engineer, so you can solve problems like this. A simpler example would be something like you have a chain that's falling off a table. As the chain falls off the table, the amount of mass that is being accelerated due to gravity is only the part that's not being, the part that's like falling. That's not the way to say it. It's all being accelerated. Anyway, let me shut up. I'm going to erase this.
One of the master, I think it was one of the master physics problems in the last set where it had a rope
Uh-huh.
that was sliding off.
Yes, this is true. But that one you could solve that one without momentum though, right? I mean, I guess this is the thing is a lot of these problems that we can solve with momentum, we could solve without momentum as well. But it is nevertheless an important new concept. What are the units of momentum?
Kilograms times meters.
Yeah, the units of momentum are kilogram meters per second. So like the units of force gets a name. It's a Newton, right? But there's no name for like the momentum units. They're just kilogram meters per second. Like a Newton meter is a joule. But unfortunately, there was no Mr. Momentum as far as I know. You know. Okay, so moving along here. So we should talk about the center of mass concept. And let me just be specific here. So here's the definition. If you have m sub I at r sub I, what? What? Okay, that's if m sub I and is at r sub I for I equals to 1, 2, all the way out to n. So suppose we've got n particles. All right, here's a picture, roughly speaking. So like here's m1, here's m2, m3, and so forth and so on, mn. So each one of these has a position vector relative to an origin, relative to the origin, R3, all right, Rn. So suppose you have n masses. They're at these points, all right? Then the total mass, well, I'll just call big M, is the summation I equals 1 to n of m sub I, right? Which is just a fancy way of writing m1 plus m2 plus dot 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 plus m sub n. That's the total mass. The center of mass, which I'll use a big R for, is equal to 1 over m times the sum I equals 1 to n of m sub I, R sub I. Would you like me to make it a weighted sum?
Depends what that means.
Well, here's a horrible joke. I'll make it a weighted sum. Check it out. Behold, it is now a weighted sum. So I can say it's a weighted sum where the weights are weight?
Fair.
Okay, yeah. So yes, the more weight the mass has, the bigger the mass has, the bigger, the more we consider the position of that essentially in this construction, right? So that's the center of mass. Center of mass vector. All right. So this is what it looks like if we have a finite collection of particles. What if instead of having a finite collection of particles, you have, oh, I don't know, something like this. Like some sort of curve where you have like a little dm over a little arc length ds. Well, and then you could say lambda is dm ds. Lambda is dm ds. That's the mass per unit arc length. You could do that. In this situation, the total mass would be the integral along the curve of lambda ds. And in principle, the mass density could be variable, right? So you could calculate the net mass of a line like that, the curve, in this way. And if you were to do such a thing, then in this case, the center of mass of the curve, instead of doing a finite sum, we do what? We replace the summation with a continuous sum, in particular, the integral over the curve of r dm. Where here I'm just, this would be like r. So you could calculate something like that. So if this is just one-dimensional, right? Now this specifically means 1 over the total mass, the integral along the curve of, lambda times the r vector ds. Like that's how you'd actually calculate that. You do the arc length integral. All right. What if the mass wasn't along a curve though? What if the mass was distributed over some plane? What would that look like? Right? What if instead of being over some curve, you have the mass is distributed over some plane, let's say, right? So you got the mass over the plane, and we usually use sigma for the mass per unit area. Mass per unit area, the area density of the mass. Well, in this case, if the area of this region is, let's say, R, then the net mass, we would do the double integral over the region R of dm. But how you actually do that is you integrate the mass per unit area times dA. And that would be how we calculated the mass of something like that. And if we wanted to calculate the center of mass, we could probably talk about, for example, x center of mass would be 1 over the mass. We take the integral of x sigma dA. The y center of mass, 1 over the total mass, the double integral of y sigma dA. And if we were talking about in 3 dimensions, then we could add a z to this as well, right? And if you want to be fussy, you could, instead of doing just an area integral, you could talk about the so-called scalar surface integral. That would be the center of mass. Again, this is just the continuous extension of the finite sum to the concept of center of mass. So we can talk about center of mass of a collection of finite points, a line, a curve, an area. What's next? Yeah.
What is the double integral?
The double integral is the integral over area. Yeah. Mm-hmm.
Do you have to know how to do that?
I don't know. I mean, sure.
Like, why is it going to be on the test?
Thank you. Yes. So you have not because you asked not. Let's see here. I don't know. That kind of depends on what's in the homework, doesn't it? So on the other hand, if we have a solid region, this is a class on physics. Physics is 2 and 3 dimensional. Do you not want me to talk about 2 and 3 dimensions in here? Really? Like, of course you want me to talk about 2 and 3 dimensions. Like, come on. Anyway, so here if we have a volume, the density in terms of volume is dm. No, I don't actually test you on specific 2-dimensional integrals. Like, there's only so much time in a semester. I cannot teach 2-dimensional integrals. I cannot teach double and triple integrals in their totality in here. We can really do specific special ones that are based on, like, methods of integration you've already seen in Calculus 1. For example, you talk about the method of washers, the method of shells. We can modify those methods to physics. We can do those things here. All right, so moving on. We can talk about mass per unit volume. This is the mass density. In this case, the total mass would actually be the integral over the volume, V, of rho dV, right? That's how you would calculate the mass in that context. In this context, the center of mass would be 1 over the total mass times the triple integral of x rho dV. And likewise, the y center of mass, 1 over mass, the triple integral of y rho dV. And z center of mass would be 1 over the total mass, triple integral over the region of z rho dV. All right? So yeah, I mean, fair enough. For complicated areas or complicated volumes, we do need methods of calculus 3 to actually be, make good on these calculations. But if the volume is sufficiently simple, you can still hack it without having calculus 3, because it really is just the infinitesimal method we cover at the end of calculus 1 or parts of 2. Now, so my point to you is there is a continuous extension of the center of mass concept, both for like curves that are extended through 3 dimensions, for planar regions, and also for volumes. The center of mass concept we can extend to any physical object, be it 1-dimensional, 2-dimensional, or 3-dimensional. This is my point, all right? And so, so why do we care? Like, what's the point of calculating the center of mass? I mean, we could do that. Let's do it. And then I'll talk about the point. Excuse me. Over here. The juice. Now, oftentimes, if I ask a question that's about like center of mass for a 2-dimensional or 3-dimensional region on the test in here, it's almost certainly the case that you have to be able to solve such a problem using methods of symmetry. All right? So like, we can do some of those examples very easily. So example 2, suppose I have a region and it's like a square here. That's supposed to be a square, if you can use your imagination. This point, let's say, is 2, 1, and this point up here, I guess I'm making the length of the side 2. So we've got like 3, 1, and then this would be what, 3, 3 in meters? All right, so suppose that this region here, so uniform density, so sigma, maybe it's 3 kilograms per, square meter, whatever. Where's the center? Yeah. Oh, well, thank you. So then what? Where's the center? Yeah.
Do you want that to be a square? Or
I was trying to make it a square. Did I do it wrong?
I think it should have a 4 in that. Instead of
Oh, yes, thank you. I was trying for a square. Any other corrections? No? Okay. So what's the center mass? And sometimes I put like RCM for center mass. So do we need to do the double integral? I don't think so. I mean, you can figure it out by just symmetry, right? It's the middle. It's right smack dab here. When you integrate, when you do those integrals, what you're doing is you're averaging the x position over the area, right? But that integral actually accounts for the object being more massive at certain points. So if it's more massive at certain points, the integral reflects that fact. But if it's uniform density, it's the same. The question is, what's the geometric center of this, all right? And so the geometric center is just that point, which is where I heard a 3, 2. I'll trust you guys. So there you go. So there's one. Example 4. What if I had like this line segment from, say, -3, -1 up here to, I don't know, 6, 10, and I'm in meters again, all right? What's the center of mass for assuming, again, this one here? I'm going to assume that the lambda is, let's say, 10 kilograms per meter, and assume it's got a constant mass density. Where's the center mass? We don't need to do the calculus here. We can just use common sense for this one. So it's the middle, the midpoint, right? What's the midpoint? How do you find the midpoint? What you do is you take the points, you add them, and you divide by 2. So the center of mass here would be 1.5, 4.5 in terms of meters, right? Now here's the deal. Conceptually, this rod of length, whatever that is, it's equivalent to a single mass at this point. So like this is, you can think of the rod as point mass at this point. All right. What would the mass of that? What would the point mass be? So what's the total mass in this case? We just do the mass density times the length, right? That makes sense because it's uniform mass density, right? If the mass density was varying with the point, then we'd actually have to do calculus. I'll do calculus in the next example. So here, what's the length? I told you it's 10 kilograms per meter, right? What's my length? I don't know, square root of something, right? Looks like I've got 6 minus 3 is 9 meters squared. And then I've got 11 meters squared. So what's 121 plus 81 square rooted?
14.
You got 14.213 kilograms. So there you go. It's, in some sense, you can ignore the fact that the mass is spread out, and you can just think of it as a single mass at that center point. With respect to certain questions, yeah.
So I don't follow where the 11 came from.
Oh, that's the, so this is the square root of the x. So like x, I went 9 over an x, and I went from -1 up to 10, so 11. So I'm just using the, you know, that thing. What's that thing called? The, what, Pythagorean theorem? Yeah, yeah, distance formula. All right.
Shouldn't that be 9 though? 'Cause it's negative 1, not positive 1.
Okay. Now, all right, I'll come back and do a calculus example another day. I'm not going to do it at the moment because I want to talk about the theory here a little bit more. So,
Oh, crap. I didn't.
no, that's easy enough to fix. It was 142.1. There we go. Right? Anybody? 142.1? I think that makes sense. If it goes over, if it goes up 11 and over 9, like 14 seems like a reasonable length. And then times 10, 142.13. All right. So we'll talk more about center of mass calculations and specific examples in a future class. But while I have this stuff on the board, I need to talk about an important theorem. And the theorem is this. It's a very important theorem. It's what we call conservation of momentum. And so I need to. Oh, very disturbing.
Sorry.
It's okay. Aye, aye, aye. So let me get rid of this. So let's derive some things. What is the velocity of the center of mass? The velocity of the center of mass would just simply be, by definition, this. So this is the definition. Here's the velocity of the center of mass, dr dt, right? And so you could just differentiate that, and what do you get? So you got 1 over m. We're going to assume the masses are constant, okay, for this derivation. And you've got the sum, I equals 1 to n, of m sub I dr dt, like that, right? So what is that? This is exactly the velocity of the ith particle, right? Now, if you brought the mass inside, we could write this again as what? This is really, all right, fine. I mean, this is fine. We could also talk about the net momentum of the system. The net momentum would be the total mass times the center of mass velocity. So again, this is center of mass velocity. And here, this is the center of mass momentum. Or you could also call this the total momentum for the system. This is the total momentum. And what's the formula for that? Well, if you look at that, the m's, they be canceling. And if you just, assume that the point masses are constant, you could rewrite this as ddt of m sub I r sub I, the m sub I r sub I, right? In other words, this is equal to the sum over I equals 1 to n of p sub I. So what I'm trying to tell you is that you can calculate the total momentum 2 different ways. On the one hand, you could just add the momentum of all the particles in the system. That would give you the total momentum. Or you can calculate the velocity of the center of mass, right? And multiply it by the total mass, and that will also give you the total momentum. Either way, same thing, logically consistent, all right? So then what? We don't just stop there, right? We're interested in Newton's law. So what should dp dt be? What's the time rate change of the total momentum? So we can do what? We can say well, that's equal to, differentiate this right here, and we've got the sum, I equals 1 to n of dpi dt. All right? But what is dpi dt? What did we talk about earlier today? We talked about Newton's second law, right? For a constant mass, which we're assuming that these n masses are constant, right? That has to be equal to the net force on the ith mass, right? So this right here is equal to the sum, I equals 1 to n, of the net force net on the ith mass, right? For lack of a better notation. Now, it's helpful for me perhaps to draw the picture again that I foolishly erased. All right. So if we think about this, what's the deal with if we think about the different masses, right? You have mass 1, mass 2, somewhere out here. Here's the ith mass, and here's the jth mass. Okay. What's the nature of the forces? So of course we could think about a gravitational force, right? Maybe there's like a gravitational force of the ith mass on the jth mass. I mean, that would be a force to think about, right? Gravitational attraction. If we knew about electric forces, there could be like an electric repulsion. Maybe this has a charge, that has a charge, so they're being repelled by, the electrostatic force that we learn about next semester. Could be all kinds of things, all right? So, but what's the situation? There's two kinds of forces, right? There is, we could talk about the force, let's say Fij is equal to the force of the ith mass on the jth mass, right? In principle, there are n minus 1 of those to consider, right? Like on the ith mass, you can think about the force that way, and perhaps this way, right? Like this, I guess this would be Ji in my notation. This would be 2I. This would be 1I in my stupid current notation, right? All right. And so if you think about it, we really have the sum I equals 1 to n, and then we've got the sum j not equal to I of what? Of f ij, right? You got that, plus what? Plus f sub I, let's call it external. There's two ways the forces come to you when you think about all the forces acting on these n masses. There are the forces which arise between the masses, and there are the forces which come from external to the system. So there's a net external force on the ith mass, and then there's all of the forces coming from the, all the other masses. But if you think about this, what's the situation here? What about Fji? What would that be? That would be the force of the jth mass on the ith mass, right? Yep.
The jth mass would be acting upon the ith mass.
Right.
So then on the diagram, would the force be Ij? Or
Yeah, it would be the other way. So the point is we have Newton's third law, right? And Newton's third law would tell me that Fji is equal to minus Fij, right? Because to every action an equal and opposite reaction. So the internal forces have to come in third law pairs. Any internal force of one on the other has a force of the other on the one. And what that means is something wonderful. In short, it means that the sum over the internal forces has to be 0. So all the third law pair cancels. This summation and its ugliness is just 0. And we simply get the sum, I equals 1 to n, of the external forces. Right? Which of course we could just call F net external on the system. So the net change of momentum, net rate of change of the momentum for a system of n particles is simply equal to the net force on the system. So what happens if the net force on the system is 0? What happens if F, the external force, is 0? The net external force is 0. What do you get? You get nothing. You get 0. That gives us what? Constant momentum, yeah. If F net external is equal to 0, then dp dt is equal to 0. In other words, net momentum is conserved. All right? Is momentum always conserved? Certainly not. But it is conserved if we are thinking about a system where the net force external is 0. The other possibility, right? You can look at it this way as well. Like dp vector is F net external, man, that's a horrible notation, dt, like this. So if dt is very small, if you like, I can instead. Let me not be so. Let me be a little bit more rigorous here. If the change in momentum times the change in time. So like this is the approximation, a good approximation. If dB dt is equal to F net, then the change in P is approximately the net force times change in T, right? So if change in T is close to 0, what can we say? Then the change in momentum is also 0. So where would that come into play? Well, think about collisions, right? So if I have a collision, right, I've got two, mass 1, mass 2. You know, this one has an initial velocity v1, this has initial velocity v2, bang. And then out comes, you know, let me say VF1 and VF2, whatever, right? So there's a collision. Collision happens very fast. In that situation, there's not enough time for the momentum, the net momentum of the system to change. So for me, and assuming this is all happening on like a hockey rink or something, or maybe it's happening in air, but the air friction doesn't have chance to slow the masses down, something like that. All right? In that situation, we can conserve momentum. So like m1v1 plus m2v2 is equal to m1v1f plus m2v2f. Right? Because it happens quickly. Now what would be, can you guys think of a situation where it wouldn't happen quickly? How about this? I guess that was example 5. Yeah, thank you. Example 6 might be something like this. I have a mass, and up at the top of the trajectory here, you know, it's got initial velocity v naught at angle theta, and up here it splits into 2, and you've got, you know, m1, m2 with, you know, v1 f like that, and V2F like that, right? In this case, I would have, M1 V1F plus M2 V2F minus let's see, how do I get the initial velocity? So M V naught cos theta sine theta, that gives me the direction vector that I want. So that's the change in momentum, right? And in this case, what's the force? I can only just multiply by dt when the force is constant. Like, this is only legitimate when the force is constant. Otherwise, I have to integrate. But in this case, talk about force of gravity. It's constant. It is, I'll get it eventually here, guys. 0 minus mg times delta t, right? So that is the situation. The force of gravity times the change in time would be equal to the initial momentum minus the final momentum minus the initial momentum. So here momentum wouldn't be conserved, it changes because under gravity, we're losing energy. We're gaining gravitational potential energy, which means that we're losing some y velocity in that motion, right? Correspondingly, the momentum is not conserved in such a thing because there's enough time for gravity to act, going from here to here. In contrast, a collision, not enough time, so momentum is just straight up conserved. Anyway, we're going to do a bunch of examples like these as we go on here, so that's all I've got for you guys today. I'll give you back your tests. So, yowzers.